Hi, this video is an introduction to Dalton's law of partial pressures, which says at constant temperature, the pressure of a mixture of gases is the sum of the pressures of the individual gases measured separately in the same container. So here you can see we've got two separate gases, the blue and the red. We've got a 5-liter container, and the pressures of those gases are measured individually. The pressure of this hydrogen here is 2.4 atmospheres, and the pressure of helium in that same container at the same temperature is 6 atmospheres. When you mix them together, the pressure of the two combined will just be the sum of those two pressures combined, 2.4 plus 6.0 for a total of 8.4 atmospheres. One of the simplest types of questions you'll see related to Dalton's law is something like this one. A sample of exhaled air from the lungs contains 4 gases along with the following partial pressures: nitrogen at 563 millimeters of mercury, oxygen, carbon dioxide, and water, and their partial pressures are provided. And the question is, what is the total pressure of the sample? So here I've written all of the partial pressures out, and all we're going to do is add them together to get a total pressure of 761 millimeters of mercury. And that's it. The second question reads, carbon dioxide was added to a cylinder containing 2.5 atmospheres of oxygen to give a total pressure of 4 atmospheres of gas. What is the partial pressure of oxygen and carbon dioxide in the final mixture? We know that the total pressure will equal the partial pressure of the carbon dioxide and the partial pressure of the oxygen together. I'll rearrange this equation. Here I have the equation solving for the partial pressure of CO2, and I'll just put in the values for the P total and the PO2. Once I've added my values, I take 4 atmospheres minus 2.5 atmospheres to give an answer of 1.5 atmospheres. The partial pressure of the oxygen will remain at 2.5 atmospheres. The third example reads, air is a mixture of 21% oxygen, 78% nitrogen, and 1% argon by volume. What is the partial pressure of each gas at sea level where the total pressure is 760 millimeters of mercury? To solve this problem, I started by figuring out the partial pressure of oxygen. So I took the percentage of oxygen written as a decimal, multiplied by the total pressure to give the partial pressure of the oxygen. So now I'll do the same thing for the nitrogen and the argon. Here we are. The partial pressure of the nitrogen is 78% of 760, or 590 millimeters of mercury, and the partial pressure of argon is 1% of 760, or 8 millimeters of mercury. This last question reads, a chemist obtains 375 milliliters of oxygen gas collected over water at 23 degrees Celsius. The mixture exerts a total pressure of 768 millimeters of mercury. What is the partial pressure of oxygen in the sample in kilopascals? If you look at the picture here, this shows you a gas being collected over water. This is useful because if you have a container and want to be sure you're just collecting the gas in that container, if you do that through water displacement, as the water level goes down, you know that you just have that gas in the container. The problem is that above the water is going to be evaporating, and the hotter the water is, the more water vapor you're going to have mixed with your gas. So you mathematically need to subtract out the water vapor from the pressure of your gas, or from the measurement of the pressure of your gas. So I have a handout for you called the vapor pressure of water sheet. It's just a table that tells you what the vapor pressure of water is at different temperatures. Okay, what I've written up above basically tells you that the total pressure in this container is equal to the pressure of the gas you've collected plus the vapor pressure of water. And if you look at that vapor pressure of water sheet under 23 degrees Celsius, you'll see that the vapor pressure of water at that temperature is 2.8104 kilopascals. Make sure you can find that on that vapor pressure sheet. Now in the problem, I noticed that they want the answer for the partial pressure of oxygen in kilopascals. So I took the total pressure of the gas, which is in millimeters of mercury, and I converted that into units of kilopascals. Now I'll apply that to Dalton's law, and I'll solve for the pressure of the gas. So here I have the pressure of the oxygen is the total pressure minus the pressure of the water vapor, and that gives me a pressure of the oxygen, the dry gas, of 99.6 kilopascals. So hopefully this is enough to get you started. Good luck with the Dalton's law problems.